Yep. Okay, so morning everyone, and welcome to the third lecture in this tutorials sections. So as you heard from our kind of pre-lecture discussion with Greg, the great thing is about the Gaussian processes and Bayesian optimization is that this is in some sense the method developed for experimentalists. And it actually has a pretty interesting history. So if you look at the Wikipedia or fairly old literature, old in this case is probably more than a decade old, you will see that very often the Bayesian optimization based on Gaussian process is referred to as kriging. So the reason why it's called kriging is under the name of the guy named Krige. I'm not sure how to pronounce his last name correctly. And he was the person who actually developed the Gaussian processes. And the reason why he developed it was because he was a prospector exploring for gold in the South Africa. And in his case, he was ultimately an experimentalist, right? So he gets to run the experiment, which is to explore the specific location for gold. He is very well aware of the cost of the experiment because kind of digging a hole in South Africa, somewhere in the desert, is ultimately a very significant investment of your time and effort. So he was very strongly motivated to make a mathematical tool that actually works and is convenient to use. So thankfully, we don't have to develop the methods under the same environment, but very often we operate also with the with very expensive experiments. So anyway, today we are going to talk about the noise-aware Gaussian processes, and then we'll move towards the Bayesian inference and probably the structured Gaussian processes. So let's see how the time aligns. So first of all, let's briefly recap what have we explored in the previous lecture. So we introduced the general concept of the Gaussian process. As I mentioned several times, if this concept feels to be counterintuitive, sort of very weird, a little bit orthogonal to the normal way how we think about the science, that's great. That means that you are starting to understand it. So Gaussian processes for experimentalists is all that. So we talked about the kernel and kernel parameters. So we talked about the kernel priors. We talked about the noise priors. And we talked about the posterior. So basically, on the very simple level, the idea of the Gaussian process is that we can imagine that we have some ground truth function. So we don't know what it is. So in case of Krige, that was a distribution of the gold in the desert. In our case, it can be the distribution of useful properties across the combinatorial spread library or any other parameter space we are interested in, like the optimal sweet spot for the film deposition and the parameter space of the deposition system. So any system that has a control knobs, control knob means having a parameter space. So Gaussian process and Bayesian optimization are the ways how we make things work in case we have some form of the parameter space in which we want to optimize. We assume that there is a ground truth function, which basically tells us, which determines the ground truth system behavior. This is what we want to know. We either want to know what it is across the parameter space, so this is a discovery problem, or we want to optimize the function, for example, find the minimum. This is the optimization problem. So we don't have access to this ground truth function. In fact, we want to either discover or optimize it. What we can do, however, is to run the experiments, meaning query this function in the chosen locations. So what the Gaussian processes does, it allows us to sample these functions in the chosen location and then interpolate it in order to get a surrogate model. So the model that we think represents the behavior of the ground truth function. The unique thing about the Gaussian process is that it allows us to create not only the not only the surrogate model, it also gives us the uncertainty. So uncertainty is typically shown as this kind of red windows around our posterior mean function. And with the knowledge of the predicted function and the uncertainty, we can run the Bayesian optimization. So Bayesian optimization comes with the acquisition function. So we have we have to specify what do we care about. So the acquisition function can favor the exploration. So if we want to explore, we don't care about where the maximum and minima of the function. What we do care about is to discover the function as close as possible to the ground truth. So typically, in order to do that, we can simply use the next measurement point chosen in the location where the uncertainty is maximum. There are other ways of doing it. So I've showed you the maximum uncertainty. There are other ways of doing it through the knowledge gradient and so on and so forth. But the idea is in all cases is that we want to discover function in the smallest number of steps. We do know that the Gaussian exploration process will always converge. The only question is how fast. In theory, this is less important. In experiment, it is super important because each experiment is the time in the lab, equipment, people's time, and so on and so forth. So we should care. The way this process happens depends on how we choose the parameters on the kernel and noise. So classically in the Gaussian process community, these are often treated as the adjustable parameters or hyperparameters you want to optimize in order for the process to work faster. In experimental sciences, this is probably not a very good approach. So it is much better to have these parameters as reflective of our experiment as possible. So for example, the noise prior is not hyperparameter, is actually the measure of the performance of our instruments. So we can also run the Bayesian optimization as the optimization when we try to find the minimum of the function. So in this case, there is a real probability of getting trapped in one of the metastable minima. So exploitative strategies often get trapped. How we are going to, and then there is no guarantee that we will ever get out of the trap. In fact, it's easy to show that sometimes you get trapped and you will just stay there forever. So how do we fight with the traps? We actually need to tune our, get the model system where the ground truth is known and we think is close to what we are interested in, and tune our algorithms on those parameters that can be tuned in order to work well. Generally, the way things can work is that if you choose the acquisition function, you can actually change how greedy it is, start with the pure exploration, and then narrow down make it progressively more greedy. So then in the beginning, you will be exploring the full parameter space, and then you will start to kind of focus on the minima. So I have also shown you that it is relatively straightforward to take the Bayesian optimization and add cost to that, because sometimes the cost of the measurements are the same over the whole parameter space. Sometimes the measurement in one region of the parameter space can be more expensive than the measurement in the different region of the parameter space. This cost can be ascribed to the parameter, so it can be known in advance. The cost can be discoverable, so there is no reason why we cannot get a second Gaussian process that tries to build the cost model, and then we can use the cost predicted by the cost model as the part of the acquisition function of the first one. The cost can be more complex thing. For example, the cost can be associated not with the absolute value of where you are in the parameter space, but the cost can be associated with how far you can move in the parameter space. So this start to depend very strongly on your specific instantiation and your experimental situation. The important thing is that no matter what the cost is, it is relatively straightforward to make it as a part of the discovery process. So it's not terribly complicated. So what I would like to start with today is the question that Remy has Okay. So, I mean, yes, if you want, please feel free to ask a question.
Hi, how are you?
Pretty good.
I had a question about this uncertainties. So in your slides and your previous slides, basically the question was how physical are these uncertainties? Because like in this specific case, it seems that that some regions that are actually should be highly uncertain, they're not, and vice versa. And look, given that this is like a numerical method, it's understandable, but generally how trustable are these uncertainties? Because I believe like one of the important aspects of using like Gaussian processes is the uncertainties associated with the measurements.
Okay, so I'll show you in the next few slides and collabs how to introduce the uncertainties from the measurements directly. So the issue of the uncertainties that are predicted from the Gaussian process itself, that's a very good and very subtle question. So the process GP predicts the uncertainties based on two things. So based on the data that we provided to it and based on the priors that we specified. So practically another thing that would be important is the mean function, but we'll get to that in a few minutes in one of the next lectures. So practically, these uncertainties are just a guide for our surrogate model. They are not absolutely correct. Unfortunately, this is kind of a nature of the scientific process, is that we can always we can never claim to get the absolutely correct uncertainties because they are not defined in a very good way. So imagine that this function here had a delta function that goes very, very low, right? In this case, Gaussian process would never be able to find it unless it hits exactly this location. So we always have to make some form of assumption about what goes on in order to be able to formulate these exploratory policies. The good thing is that the human brains work in exactly the same way. We typically have to have some surrogate model of the future in order to be able to plan our actions. And, you know, the more we know, the better our model is. So in this case, they're exactly kind of similar to how the humans operate. Make sense?
Makes sense. Yeah, thank you.
Notice one other very important thing. So I'm going to show the Bayesian optimization based on the Gaussian processes only, but in principle, we can substitute Gaussian process by any other algorithm that gives us the prediction and uncertainty. It can be ensembled network. So if you have a neural network, it gives you one prediction. If you have 100 copies of the same network and initialize them differently, you will have ensemble networks. You can average the prediction and get the prediction and uncertainty. You can incorporate physics in the network. So it can be the physics-informed neural networks. They also give you prediction and uncertainty. I'll show you how we can use Bayesian inference, which also can give you prediction and uncertainty. And then there are many other ways of doing it, like conformal prediction, so on and so forth. So the reason why I personally like Gaussian processes is because they actually come with a very clean physical picture behind them, meaning that it is possible to develop a kind of explanatory theory about how they work. And it's possible to develop an intuition about how they're going to behave in these specific scenarios. If your knowledge of physics, and also I'll show you how the Gaussian processes can be extended if we understand the physics of the system. So, but that's a personal preference. There are a lot of people who will swear by the conformal prediction, and ultimately it depends on the domain. For example, the Gaussian processes are arguably the best tool in cases when our parameter spaces are continuous and we expect some physical laws working around them. But if our parameter spaces are something non-differentiable, that like molecular spaces or process optimization spaces and so on and so forth, it's entirely possible that GP is just not the best algorithm there. It's kind of one of these manifestations of the no free lunch theorem, which basically says that there is no optimization algorithm that is always the best. You always choose the right one for the specific application. So anyway, speaking about the noises. So on the last lecture, Remy asked what happens if our noise is not constant across the parameter space. So here we explicitly assume that there is a single noise function that describes the noise everywhere. We also assume that the kernel is translationally invariant. So neither of these considerations is baked in stone. So first of all, kernel can be dependent both of x and x prime, so it can be not translationally invariant. And of course, there are a lot of ways how you can adjust the Gaussian process for the scenario when the kernel is partially sort of almost translational invariant, but not quite. It's called the space warping approaches. So I'm not going to talk about it, but this type of solutions exist. And the second very important consideration is that if the noise depends on the position in the parameter space. So generally, by definition, we know that the way GP works is that we assume that there is some ground truth function. We don't have access to it. We can only measure it with some noise. So that's what we use for GP. The question becomes, can we adjust this situation for the scenarios when the noise is also positional dependent? So this is possible, and the one way to incorporate the variable noise is through what is called the heteroscedastic Gaussian process. The idea behind the heteroscedastic GP is very simple. It basically uses the Gaussian process for a function, and it creates another Gaussian process for the noise. So basically, it creates two models. One model is for the function itself, another is for the observational noise. The important thing is that classical implementation of the heteroscedastic GP will assume the zero mean function for the function itself and for the noise. So this is how classically the GP communities work. It doesn't have to be this way. So the mean function can be something else. So I'll show you it in the next example. So one of the notebooks that I have shared with you is actually the instantiation of the heteroscedastic GP. So it is on the GitHub currently, so you can see it if you go to the GitHub for the course. And this is how it looks like. So I'm not going to run it because it is fairly time-consuming, but just as a sort of what you should be looking at. So we install the gpax, we import it, we define the ground truth function. So the ground truth function we define with the function itself, and we also define with the noise, which is position dependent on each data point. So if we plot our true function, this is how the true function look like. So this is the red curve. This is the measured observations. And this is the scale bar is the noise at each measurement location. The algorithm does not have access to the noise in this case. The algorithm has access only to the measurements at the specific locations. The reason why this heteroscedastic approach can work at all is because you can see even by eye that here the points are laying on the smooth line. And here you can see that they kind of become a little bit more erratic. The way that we can realize the heteroscedastic GP is through this function, so please feel free to play with it. The output is going to be the parameters of the kernel, so the kernel length, the kernel noise length, and then the kernel noise scale and the kernel scale. So as I said, it works by creating two Gaussian processes, one for the function itself, another for the noise. The way that we plot the data is very straightforward. So as the output, we are going to get our predictive mean, which is our surrogate model. We are going to get the predictive uncertainty. So that's exactly the same as the normal GP. But we're also going to get the information about the noise. And what you can see here is that this is our actual noise. So the noise that we provided as the ground truth to the system. This is the rhombuses is the inferred noise. So this is the noise that the system has discovered. And the blue interval, this is the noise that the uncertainty of the inferred noise. So you can argue that in this case, there is a very real risk of mixing the true behavior and the function behavior. That's absolutely true. So there is once you run the heteroscedastic process, there is a very strong balance between your priors. So if you want to experiment with that, we can define the noise priors using the GPAX function and see how it affects the noise reconstruction. So for example, if I postulate that my kernel length for the main function is very small, then the algorithm is going to take all these wiggles and assume that they're real and not interpret them as the noise. At the same time, if I postulate that the kernel length for the main function is actually fairly large, then the algorithm will say that these wiggles are noise, but it will also be tempted to interpret these wiggles as the noise and assume that the function itself is smooth. So that's a kind of was a great thing about the heteroscedastic GPA, but it's also the limitation that you need to be very, very careful about. You need to be very, very careful about what you consider to be the true function behavior and what kind of gets classified as the noise behavior. Because for us, it's obvious we created the ground truth. But for the algorithm, the same feature can be noise or the true function behavior. And the way that we can control that is by providing priors. Make sense? So another thing which is very important and can be relevant in some physical systems is that we can introduce more complex connections between the noise and the function. So for example, I'm not sure whether it will ever apply to the experimental measurements, so maybe it is, maybe it is not. But at least if we try to do something in the theory domain, imagine that I want to use the Gaussian process to explore the behavior of some statistical physics model. So in the statistical physics model, like Ising model, I expect that certain parameter will peak close to the phase transition. But I also know that the noise involved in the determination of this parameter will also peak close to the phase transition. It's just the way the statistical physics work. So in those cases, I can build some form of relationship between the noise function and the discoverable function and say that noise is always higher if the function itself is higher. So this link can be rigid, and then I can use the version of the GP that I have now. This link can be correlative, and then I can use the multitask Gaussian processes, and I'll show you how to do that in probably lecture number 5. So then there are other situations. So for example, in many experimental scenarios, the experiment can be configured in such a way that the noise can be measured or estimated. So our team have encountered this type of scenarios in the case of both non-indentation measurements and scanning probe microscopy measurements over the combinatorial libraries. So very often going from one part of combinatorial space to another part of the combinatorial space takes a lot of time. At the same time, doing multiple measurements at the same part of the combinatorial space, for example, do the non-indentation on the 5x5 grid, is relatively fast. So in these cases, it makes sense to configure the experiment that we do multiple measurements at single location, and essentially we get access both to the function and its noise. I'm sure that there is a scenarios where the noise can be estimated even in single measurements. So for example, when I run the scanning probe experiment and I try to average something over the image, for example, surface photovoltage for the discovery of the combinatorial for exploration of combinatorial libraries of hybrid perovskites, I can use the dispersion within the image as effectively a measure of the noise for specific concentration. So notice that if we measure both the function and the noise, we still need to create the function. We need to create some strategy that will predict what would be the noise in the different locations. So let me show you the example again of the notebook where this approach is realized. So this is the notebook number 5, which is also sitting on the Colab. So if you, this one should run much faster, so please feel free to experiment with that as you kind of go on. So what you see here is the example of the function with the measured noise. So this is a modification of the Forrester function. So kind of one of the classical functions for the check of the 1D Gaussian processes. We also add the noise to that. So the visualization in this case is very straightforward. So the points are what we measured. The lines or the intervals, this is essentially the noise. So the difference compared to the heteroscedastic GP is that in this case, the noise is measured. In heteroscedastic, it is inferred from data. In this case, the noise is given. So we can realize the Gaussian process with the measured noise. So it is also realized through the measured noise GP in the GPACs. Again, if necessary, we can provide the priors on kernels and so on and so forth. In this case, we just skip this part. So now the output is the same as for the normal GP. It's the kernel length, kernel scale. The noise in this case, as you can see, is 0, and the R hat and the N effective for noise is none, just because noise is not a part of the equation. So we are not trying to fit the noise. We already know the noise. Once we have that, we can actually make a prediction on the denser grid, so the usual interpolation for the GP. And this is how it's going to look like. So this is the measured points and the noises in these measured points. The dotted curve is the ground truth function. The blue curve is the posterior mean. So this is the interpolation. The red is, as usual, the model uncertainty. So important thing here is that there are several ways how we can incorporate the noise prediction. So currently we use either the linear regression method, so it assumes that noise is linear across the parameter space, or we can say that noise is interpolated by the Gaussian process, then it would be a not linreg, it would be a GP-reg. So there are two options here. More complex functions can be added if it is necessary. So as I said, the reason why we need to specify the noise prediction method is because we know the noise only at the measured locations. When we use the Gaussian process, we try to make a prediction in the all other locations, so the unmeasured locations. But to do that, we need to have a model for the noise. So we need to know how noise behaves across your parameter space. So one way we can do it is through the linear regression, assume that noise is a linear function of the control parameter. Another way to predict it is assume that that noise is also Gaussian process. Again, remember that this is different from the heteroscedastic case because noise is given, we just interpolate it, whereas in the heteroscedastic case, the noise has to be discovered. So this is the example of the predicted and measured noise. So this is the predicted noise. Remember that this was done with the GP-reg. So I can run it, and we'll see how it is going to work with the GP-reg argument. And while it is doing it, let's see what else the algorithm can do. So we obviously can run the same type of algorithm in the form of the Bayesian optimization. It doesn't have to be, if we have Gaussian process, we always can build a Bayesian optimization loop on top of that. So this is, in this case, I have modified the function a little bit just to kind of play with the interesting behaviors. So you can see that now the function has points which are fairly high with the small noise and points which are fairly lower, but with a much larger noise. So what we are trying to do now is to run the Gaussian process optimization and see how the discovery process is going to work. So this is our starting point. So again, I obviously go through these notebooks much faster than it is possible to go through the code. But they are made to be sufficiently detailed that you should be able to run them and experiment with the different parameters. So what I'm trying to do is just to highlight what is important and what goes on. So in this particular case, you can see how the Bayesian optimization starts. So this is our initial guesses about the kernel parameters and the noise distribution. So this is the ground truth model. This is the surrogate model. These are the model uncertainty. So in this case, we also generate the model for the noise. So this is our predicted noise, and this is our measured noise. So notice that the noise is interpolated pretty well. Then we form our acquisition function, and in this case, we want to, so the way that you check what is actually has been going on is that you look what acquisition function has been used. So in this case, we use the expected improvement. Expected improvement is a fairly greedy function. So it's not a discovery, it's a pretty greedy optimization. So you can see that it has calculated our acquisition function and have chosen to make the next measurement here. So it makes perfect sense. So we took the next measurements, we recalculate our model. So now this point is correct. Our noise estimate is still kind of pretty good. And as you can see that now we recalculate the acquisition function, and the next exploratory point is chosen here, because here the noise, the ground truth values is fairly low, but at the same time noise is sufficiently high that the algorithm feels that this should be the next point to explore. And that's what it does. So now we again recalculate our model, we recalculate our noise model, and then the process kind of start to keep exploring this part of the parameter space for quite a while. So as you can see, the next several steps are going to be all exploring locations here. And the reason why it is done is simply because the noise here is high. And the algorithm says that, okay, if this point didn't work out, maybe I should look next to that. So it's given the very high noise, it tries to keep exploring this part of the parameter space over and over again. And that will last for quite a while until the interesting points in this case are completely exhausted. And then the algorithm will say, you know what, I didn't find interesting locations here. I'm going to explore back to the this part of the parameter space. So notice that this behavior, when you start exploring points very close to each other, can be, in many scenarios, not what you want to get. There are ways to get rid of that. The simplest way to get rid of that and favor the exploration across the parameter space is to introduce some form of the discount factor. So basically, the way it works is that you can simply create a Gaussian function with the width equal to your kernel length, and then you subtract this function from your acquisition function. Once you do that, then all the points next to your measured point are simply not a part of the consideration. You just discounted them. However, you basically relax this discounting with the time. So at the first time step, you discount with the coefficient 1. At the second step, you discount with the coefficient 0.9. Then you can make it 0.9 square. So basically, the discount becomes less and less significant with time. And after several iterations, you can actually go back to explore those locations if you still feel that they're interesting. This is not very difficult to realize because, as you can see, the structure of the discovery loop in Bayesian optimization is fairly straightforward. So all you have to do is to find the place where you have your acquisition function. So in this case, it is here. And then you check what is the format of the acquisition function, and you simply create your own loop for the discounting factor. So it's pretty straightforward, and depending on the environment, it can be the right way of doing things. So this being said, let's go back to our simple GP example. So here you can see that it is converged, and we got the estimate for the predicted noise function versus the measured noise function. So then this notebook, just out of curiosity, has this instantiation of the same approach where you postulate that the predicted noise is linear. And as you can see, it actually didn't work particularly well. So in this case, the noise model ended up being very different from the actual noise. So sometimes it kind of happens, but at the same time, for the optimization process, it didn't measure that much. So we found the maximum as we wanted. So make sense? So let's go back to the PowerPoint. So I've shown you the example of the measured noise Gaussian process regression. So these are the two examples of the function when the noise model was either GP or noise model was linear. Again, remember that we do need to have the noise model because we need to speculate what the noise would be in the non-measured part of the parameter space. So the next thing that I wanted to show is the scenario when the measurement locations are not very well defined. So in most cases, we assume that we know exactly where we are in the measurement in the parameter space. That's not always true. So for example, if we work with the system like combinatorial library, we know what compositions we want to create, but we are never certain that the compositions are exactly what we want them to be. So in this particular case, we have two choices. So choice number one is to run some experiment that allows us to calibrate the composition of the local location, for example, through the ADX or ADS, sorry, or any other compositional measurement method. The question becomes whether we have these facilities in-house, how expensive it is, and how precise it is, because many of the elemental measurement methods also come with a certain uncertainties, because the elemental sensitivities factors can depend on the local compositions as well. So if we want to deal with those type of problems, we can deal with the Gaussian process with uncertain inputs. So this is a kind of very recent adaptation made by Maxim as the part of the GPAX, again, because this is something that we needed as the part of the experimental research. So this is what we call uncertainty input Gaussian process model. So we assume that there is some uncertainty in the position. So for the time being, it is just a pure noise type of function. And this is the example of how it is implemented and how it operates. So as usual, we import our GPAX and do all the installation. We create our ground truth function. So in this case, the function is still relatively simple Forester, but we assume that our X positions have been shifted compared to the original values. So we assume that some of the noise comes because the X are not exactly what we think we are. And of course, some of the noise is associated with how the function is measured and the general function variability. So as the next step, we need to define the length priors. So in this case, we have priors on the length scale, priors on the noise, and it is very, very important to introduce the priors and be very cognizant about where we come from. Because if we say that our priors of X are very large, meaning that we don't really know how the measurements were taken, it's not going to work particularly well. So it's very important to be kind of cognizant about how these are done. And generally, based on relatively limited experience working with this uncertain input Gaussian processes, for the time being, the advice that, or the kind of rule of thumb that we have is that if we run the normal Gaussian process when we introduce some noise associated with the measurement in the y direction, so the noise associated with the measurement, it is usually a good idea to make it maybe twice larger than we believe the instrument can perform, just to account for the factors that we don't control very well. For the uncertainties in the position in the parameter space, so the position of X, I have a strong feeling that it is better to be optimistic. because if you are over-optimistic, things converge. If you are pessimistic and say that I really don't know where I am in the parameter space very well, the Gaussian process start to behave very, very poorly. So the idea is that kind of sometimes it's good to be somewhat pessimistic. Sometimes it's probably a better strategy to be somewhat optimistic. But this is how it will work. So this is the realization of the classical Gaussian process using the exact GP method. So one-dimensional matter kernel, whatever the length prior and the noise prior we defined. So output would be kernel scale, kernel length, kernel scale, and noise. So then we can do the interpolation over the full parameter space. In this case, we don't know what the, we assume that there are no uncertainties in the X position. So for the uncertain inputs, we basically use the different version of the Gaussian process, which is UEGP. So we explicitly specify the priors for noise for the X scale. And once we run it, this is kind of going to be our output. So we can incorporate those things. So this being said, any questions about the noise in the Gaussian processes before we go to the next topic? Okay, so good to go. And as I said, the most important thing is that, and that's sort of something that if it is a take-home message from this set of lectures, then we are all successful, is that Gaussian process is not a black box algorithm that you can magically connect to your system and get an active learning. It actually will work for most simple scenarios. Like if you want to use the Gaussian process to explore a single combinatorial library or to optimize the deposition condition, most likely out-of-box GP will work. And it doesn't require a lot of time to set it up because finding people who can use it in the scikit-learn or jkopt or any other optimization library is not that difficult. And it will work remarkably well. However, beyond the simple cases, when you have costs, when you know something about the noise structure and so on, and all of us coming from the experimental side know very deep details about how our systems work and operate. So in those cases, using the out-of-box GP can bring the disappointing result in a sense that it will not give any better result than the human operator. In fact, very often it will take longer. However, a well-tuned Gaussian process, when you tune it based on your knowledge as the human operator to your specific case, will probably work much better than the human operator. But the difference is going from simple GP methods to the ones when you actually kind of control what goes in and what happens inside. And then we are in a position when we actually can build upon these simple methods in order to realize much more complex workflows with the multiple moving parts.
Sergey, this is Remy. I have a question on this.
Sure.
So if I understand correctly, you're saying we can constrain our GP process with, let's say if we have like a rough idea of like what the ground truth should look like.
Yep.
You don't know exactly. You see, I think it, it should follow like some sort of like a functional. You're saying we can constrain the GP following that functional?
So for the time being, I showed the examples of how we tune GP depending on what we know about the noise level of the system. In the second part of this lecture, so we are going there, and the lecture on Wednesday, I'm going to show how we can introduce the physics model as the mean function of GP.
Okay, great. Okay, yeah, okay. I just wanted to clarify and making sure I was like following your train of thoughts here. So that's thanks.
So, but as I said, the important thing that even noise matters. So the problem is that once we start to add physical model as the part of GP, it becomes super powerful, but the physics model comes with the prior and GP comes with the priors.
Mm-hmm.
And unless we know what the priors do for the GP, we can simply kind of disbalance the whole thing. So you see, the great thing about using the Gaussian processes is that once we are in the lab doing whatever, we make a lot of decisions which are driven by the human intuition, right? And this intuition comes from using the tool, general physics knowledge, and so on and so forth. I mean, we intuitively have it in our mind that if we increase the temperature, the rates of the reactions are going to increase exponentially. And we usually have a rule of thumb why it is going to happen. Sometimes the physics would be not straightforward. Like if we have the PLD deposition, we know that if we change the pressure in the deposition chamber, the deposition process will change. And some of this change would be associated with whether the plume kind of spreads before it reaches the substrate or the plume actually touches the substrate. So sometimes this change can be very, very nonlinear. But there are ways to represent this knowledge in the Gaussian process. So on the one hand, represent those laws as a part of it, but at the same time, make it sufficiently flexible that they can be the exact parameters can be discovered. So let me show you kind of as the general introduction to this topic. Let's start with the kind of switch gears and talk about the very, very familiar to every of you topic, the functional fits. So that's something that all of you have encountered many times before. And we can start just reminded to illustrate what's the difference between the Bayesian inference versus the standard function fit. So remember how the linear fit works, right? So we have a collection of x, y values. We want to find the line that best represents the data. So we have a collection of points. We choose the function. So in this case, it is a plus bx. So what we want to do is to calculate the total error. So the total error in this case is very straightforward. It is essentially the difference between the actual function value, so what we measure, the function value predicted by this formula, a plus by x, and then it is squared. So if what we want to do is we want to find the values of a and b that minimize this total error. So that's very straightforward, and the way that we can do that is simply calculate this error function. It would be two-dimensional because we have only two parameters, a and b, and then the coefficient of the straight line correspond to the position in this parameter space where a and b, which is absolute minimum. So the great thing about the linear fit is that there is only one minimum in this error function, which means that if our algorithm converges, we will always get here. So this is very straightforward, and all of you know that. Typically, the way that this is realized is through the gradient descent. So we start with some initial guesses, and then we find the direction in which the function decays fastest. And then we make a step in this direction, and then we kind of keep doing it until we get to the absolute minimum. I'll show you the notebook, which actually kind of illustrates this concept. So, and it will also visualize how the fit process actually goes on. So an important thing is that gradient descent doesn't always converge to the right value. We typically don't think about it because by now the scientific software is sufficiently powerful in order to get the right answer most of the time. But the truth is that I can easily build a counterexample that will cause the function to converge towards the wrong value. So this is the example of the sine function. So this is the gradient descent, which converged to the true minimum. But notice that the error of surface in this, so there are only two parameters, the amplitude and the period. So it also can be represented as two-dimensional parameter space. Notice that in this case, the shape of this error surface is not simple anymore. There are multiple minima. So this is the example of the gradient descent that converged to the right direction. And this is the example of the gradient descent that did not converge to the right direction. So I've chosen my initial parameter values here. Gradient descent went to this point, and here it is stuck. But this point corresponds to the function that looks like this. So it's clearly not a very good fit to this particular set of points. So let me show you the notebook that you can play with where these algorithms are implemented. So let me switch to the, let me switch to the right window. So this notebook is also on the GitHub, and the sharing, here it is. It's interesting that the share the screen is marked green, which is supposedly made so you can always notice easily, which basically means that sometimes when I look for the right one, I kind of don't ignore everything which is not the same color as everything else. So this is a fairly large notebook, but it's easy to play with. So just go through the examples, and the ideal way to play with it is simply go to the code and see if you understand everything that is done here and change the parameters. So it's a simple linear fit. There is a polynomial fit function. There is an exponential fit. There is a sinusoidal fit. So notice that if I try to use the sinusoidal fit using the SciPy, if I choose if I just try to feed the data, sometimes I get a very wrong behavior. So the question is, why is it happening? And can you fix it? So I added some specific questions that you can use as the self-check guide. So this is example of the power law fit. So in this case, I made the modification obvious. So notice that this curve fit function requires an initial guess of what the parameter values are. And I have chosen the parameter values that actually don't work. So let me show you how it can be easily fixed. So in this case, our real power law is a times x power b, where a is 1 and b is square. So it's just a square law. But I choose my initial guesses as -1 and -2, and it doesn't converge. At the same time, if I choose the initial guesses as 0.1 and let's say 5, let's see what happens. So in this case, it's converged remarkably well. So the reason for that is that there are parts of the parameter space. So if we want to use the gradient descent, we need to choose the initial point from which we start the descent. Some points will lead us to the right answer. Some points will lead us to the wrong answers, and there the fit will get stuck. For simple functions, this is very easy to find the problem and fix it. For more complex functions, it can be actually super complicated. Imagine that your function is living in the 20-dimensional space and not in the 1-dimensional space. So anyway, there are a few more examples of the fits of the different functions, just so you can kind of get a hang of it. An example of the fit for the multivariate function, linear and Gaussian, and a few examples of how the process works. So this is basically the illustration that you saw in the file. This is the illustration of how the error surface look like and where it comes from. So we can, in 3D, we of course cannot visualize the surface, but we can visualize the cross sections for the surface. And this is the kind of handmade, or to be more precise, the ChatGPT made code that illustrates the gradient descent. So it basically defines the function, the mean square error, and then it calculates the gradients, and then it basically provides the learning algorithm. So essentially you find the gradient, and then you make a step in the direction of the gradient. So it shows you how the fit works for the line function, and the same type of algorithm, and it shows the evolution on the gradient descent surface. And so this is kind of illustration. It's a trap. This is how it will work for the sine function, and this is how we can get trapped in the false maximum. So this is should be fairly straightforward algorithm. So experiment with the initial values of the parameters and see when we get a right fit, when we get a wrong fit. So the question is, why do I show you this behavior for the functional fits? For the very simple reason that most of the time, we actually need to fit functions. It's simply a part of what we are doing pretty much every day in our professional work. The important thing is that typically we are using the fits using the oops. We typically use the fits using the, let's go for the, we'll move to the Bayesian inference collab next. So most of the time we use the fits done by the gradient descent. There are other methods that can be specified in scikit-learn, but most of the time we get a single answer. We also know that we do not necessarily get where we want to be. So the fit can converge to the wrong number. And in low dimensional cases, it is very easy to detect that. So we have unphysically large errors. We see that our predicted function and our data just have nothing to do in the common. Therefore, we are going to tune our initial guesses in order to get the fit that is look good and plausible. This is absolutely a reasonable strategy, and that's what we have been doing for probably several hundred years by now, since the least square methods were invented in 17th century, if I'm not mistaken. But the thing is that these errors can be a little bit more subtle. So, for example, imagine that you are doing the functional fit, and you get a value of parameter, but this parameter value is something that you know. For example, imagine that you measure the mobility in the, do the physical measurement on the silicon single crystal, and one of your parameters is the mobility of the electron mass. So the mobility of the electron mass of electron in silicon is very well known. So the question becomes, what happens if your answer, if it is a fitting parameter, what if the answer is off by 20%? So are we saying that this is not silicon, or how do we kind of deal with the uncertainty? Another example, which is actually a very beautiful example from the scientific history. Imagine that you are sitting in front of the, you have an exam, and your exam question is to measure the acceleration of the free fall. So we all know that is 9.8 meters per second square. So imagine that you have a pendulum. We know that there is a very good relation, a very well-known relationship between the oscillation period of the pendulum and the length of the pendulum. So let's assume that the length is known. So our physics exam is to measure the free fall acceleration. So all we have to do is to detect the period of oscillations. And once it is detected, we can say that do a simple algebraic operation and get G. But now imagine that G is not 9.8, but it ends up being 11. So what are you going to do? The length of the pendulum is known very well. Let's assume that the stopwatch that you have is precise, or at least sufficiently precise. So it turns out that in the historical example that I'm bringing up, the idea was that under the pendulum was a magnet that was not available to the student. And essentially that was the kind of exercise on honesty, because a lot of people measure 11 and then convince themselves that the number should be 9.8 because they know that the answer should be 9.8. But in this case, that's an exam, and under special conditions. In real life, we always have to deal with the multiple set of parameters and different degree of knowledge of those parameters that we have. So what we are going to look at now is the concept of the Bayesian inference. So we're going to look what the Bayesian inference is and how it is different from the least square fits. We are going to look at what are the prior distributions of parameters, what are the posterior distributions, and how we compare the models using the Bayesian methods. So let me switch to the Colab. So where is it? Let me switch to the Colab number 8. Here we are. So it is obviously also on the it's also on the GitHub. So in this case, I also illustrate the least square fit and the Bayesian inference. So first, let's start with an example. So in this case, we import NumPy and Matplotlib. We import the same SciPy curve fit. So let's create a data set and the ground truth that looks like this. So the ground truth behavior that we have is essentially two linear segments separated by the jump. So very, very simple. This can be anything. It can be the behavior of material under the strain, or it can be the region where there is a phase transition. I mean, all of you are familiar with the examples when some interesting behavior is discontinuous. So let's look a little bit about what the structure of this program, because we are going to come back forward and backward several times, and it's kind of useful to know what the parameters are. So the usual structure is we define our function, and we provide the more or less fixed parameters that we care about. So this is just a linear segment before the jump point and after the jump point. We define the measurement function. So what we measure is the function plus some noise. So we provide the default value of the noise of 0.1. So if there is no change of the noise, then it's 0.1. If there is a change, then it is what it is. And then an important thing that we do is we define the random seed. So typically we use 42 because that's obviously the answer to all the world's questions. And then we define the interval. And this is how we define the number of points inside the interval. So we typically take 15 measurements, and for convenience, we also add the measurements made at the ends of the interval. We don't have to do that. It's just done for the convenience of the visualization and so on and so forth. So if we measure 15 points, that the answer looks like this. If we do the measurements and we measure 5 points, then the measurements look like this. So as before, our task is to reconstruct the ground truth based on measurements. So notice that one way we can reconstruct the function based on measurements using the Gaussian process. So we just talked about it for 2.5 lectures. Gaussian process is what it is. And I'll show you the example in the next lecture of how the Gaussian process is going to work on the data like this one. But Bayesian inference is a slightly different process. It's more like a least square fit, where we have some functional form and we want to find out what are the parameters. But let's first do it with the least square. So the task is, these are our measurement points that represent the function plus noise. We want to discover the functional form that is best fit for this data. So how are we going to do it in the least square methods? So first of all, we need to define the fit function. So notice that in this case, the fit function is chosen to be exactly the same y, the same functional form as our actual function. It doesn't have to be the case. So the fit function can represent a totally different function. In this case, we chose them to be the same just to kind of illustrate the salient points of the process. So in real life, our fit function is the guess about the ground truth. It's not exactly ground truth. So then if we want to do the functional fit, we use again the same curve fit function from the SciPy. So we take our data, x, y. This is our jump function, so the function that we use to fit. And then we need to use the initial vector of the parameter values. So you can see that here we have parameters a, b, c, d, jump point. We take them 0.2, 1, 0.5, 2, 0.5. So 0.5 is where the jump point is. We fit the data to the, we fit the function to the data, and you see how the fit look like. So it has nothing, it looks nothing like our ground truth. And in some sense, this is not surprising, because we don't have that many points. The noise is pretty high. And if you look at this data, so imagine somebody gives you the data and the fit without showing you the ground truth. So in this case, you will say that this is actually not terrible. So it's kind of okay. So see what happens if I choose the initial parameter value for the jump point position to be 2.5. So you can see the jump. It happened exactly at the 2.5. So, okay. So now let's see what happens if I make it 2.8, for example. So the jump is here. It's exactly where I said the initial guess is. So the question is, why is it happening this way? And the answer is very straightforward, that if I have the point here and here, there is no way for the least square algorithm to choose the right place for the jump. It's just kind of invariant with respect to that. So I simply cannot learn what the value of the position of the jump is. And once I put all these elements together, I come with the very interesting set of conclusions. So first of all, how well my fit converges and what type of values it predicts depends on my initial guesses. I can very easily get the wrong answer. Secondly, there are, in this particular example, but obviously in real world situations as well, there are scenarios where we simply cannot do least square on the sum parameters. They will stay where they are based on the initial guess. And we can, of course, improve things if we increase the number of the measurement points. So please experiment with those and see how it affects the behavior. But in many experimental scenarios, our number of experimental points is simply limited by how expensive the data is. So this brings me to the primary limitation of the classical least square fit approaches, is that we have no way to reflect our prior knowledge about the system as a part of the fit. So the best thing that we can do is to come up with initial guesses. And if our initial guesses are close to the ground truth, we will actually get there. However, we cannot control the parameters of the fit particularly well. To be fair, there are ways to do that. So there are libraries like LMFit, for example, that allow fairly complex set of hard constraints on the parameters, but using them becomes kind of complicated. And the most important thing is that imagine that prior to starting the fit, I already know something about my function. For example, I know what approximately the values of the parameter A or parameter B can be. And then the question becomes, how can I incorporate this prior knowledge to be a part of my discovery process? So in the least square approaches, this is fundamentally impossible. There is just no degrees of freedom to do that. But that's interestingly something that we can do very well with the Bayesian methods, and specifically with the Bayesian inference. So let me show you how it can be done and how it works. So again, we do it with the GPUX because it kind of incorporates these methods in the relatively easy to use form. In principle, this type of fits can be realized using many other libraries. So if you just want to do simple Bayesian methods, the great simple library is POIMC. The very complex library and very powerful and very complex library would be BOTORCH. So again, GPUX is developed in such a way as to make these things intuitive and easy, meaning the low entry barrier, at the cost of being not scalable to the supercomputers or very high dimensional parameter spaces. So you always kind of have compromises. So let's do the following thing. So let's again create our data set. So we again have our 15 data points, 17 data points, and we have our ground truth. Now, the new thing is we introduce the probabilistic model. So what is probabilistic model? So in the least square method, we define the function that we want to fit to the data. In the probabilistic model, we define the function, and we also define the priors on the function parameters. So the function itself is just the functional form. So as you can see, this is the sigmoidal function, and you can see kind of how it looks like. It's just a sigmoid. The priors is what we know about the parameters of the function before the experiment. So where should we get priors? That depends on the experimental setting. So the priors is something that we can generate based on the common sense. For example, if some parameter can be only positive, the natural way to define it through the half normal. So half normal function can be only positive. It's basically Gaussian when the tail that goes into the negative values is kind of flipped over. If we know that our parameter can change only within some narrow interval and no more than that, then we can use a uniform distribution. So generally, uniform distribution for an interval or normal distribution are so-called weak priors. Corresponds to the cases where we as Jon Snow don't know much about the system. In the cases when our priors are weak, Bayesian methods, they're more robust than the least square fit, but they don't give us particularly significant advantage compared to the least square. The true power of the Bayesian methods is when these priors are something much more solid. So for example, if we know something about those parameters, like for example, beta 4 is the position of the crossover point. So this is something that can be known from the past measurement. And if it is known from the past measurement, for example, from the collective effort of the people in the field, so some of these things can be crowdsourced. Some of this can be determined by the literature mining. Some of them can be determined from the past data. So if something is known, then there is a huge advantage of choosing the narrow and very informative priors compared to the broad priors. And I'll show you the example of how it works. So for the time being, this is a relatively broad prior, and this is a probabilistic model because we define the function itself and we define the parameters of the priors on the parameters of the function. So notice that this function has a different functional form than this one. This is 2 lines and a step. This is a sigmoid, and sigmoid obviously has the tails which are horizontal. So this is a second function, probabilistic function, which is piecewise. So this one is exactly the same as the data generation process. Again, it is defined as the model and the priors on the model parameters. Again, these priors are open. So we have a convenient function that allows us to visualize this distribution. So just if we want to know what how this look like, we can use this dvs function in order to show what the distribution is. So how do we run the Bayesian inference? So what we need to do in this case is to define our model. So model is the probabilistic model of the physical process. We need to define the model priors, and then the fit itself is just one line of code. So we define the model, SPM, and we feed this model to the data. So notice that there are some control parameters here and some main parameters. So key is essentially the random number key. It's kind of irrelevant for our discussion. X measured and Y measured, it's our data. And these parameters are essentially the parameters that define the Markov chain Monte Carlo process. So the thing that you need to look at is this parameter R hat. It should be kind of close to 1.1 something. So if it is much more than 1, then things don't work very well. So what happened in this once we run this model? Essentially, what we did is we tried to find all possible functions that are consistent with our data, and they have the functional form that we defined, and kind of functional form and priors that we defined. So how does the output look like? So this is what we get as an output. So notice what we get in this case. We have our ground truth. This is a black line that's black line. So this is our comparison. The model doesn't have access to it, but we compare it. We compare our answers with this model. So actually this example, let me see what I've done here. Okay, so let me change this a little bit because it didn't work. I made it too restrictive at this point. So let me run it one more time. So we run the model again. We plot the predictions. And okay, so now that's much better. So see what happened. So the black line is our ground truth. So this is something that we compare things to. Notice that the primary output of our analysis is the large number of these red curves that come with the noise, and they also comes with the jumps. So these red curves, this is what is called samples. So this is the samples of what the answer can be, which is consistent both with the noise and with the model. And then we have blue line. So the blue line is the average of all the multiple red lines. So notice a very interesting thing, that the blue line essentially follows the ground truth function here and here, but here it also almost becomes like a flat line that spans this part, these 2 points. So what does it mean? It means that realistically the jump can be anywhere between this measurement point and this measurement point. And what our model does, it says that these are the possible realizations of the model of the function that have jumps in this location. And the blue line, it's the average of those points. So it basically gives us the probabilistic reconstruction of our ground truth function.
Oh, can I ask you a quick question?
Sure.
If we plotted the median instead of the mean, could it be possible that it actually captured the actual, like closer to the actual, where the actual jump happened?
So what we can do is we can kind of plot the individual functions A and B based on the A and B. So now you can see where the jumps can be. So this is the reconstruction of the posteriors with the noise, because we have the functional form and the noise. This is just the functional form. And if you are curious, we can also kind of take these red curves and create not only the average, but also the uncertainty. And then you can see that the teal curve is our ground truth, the blue curve is our posterior mean, and the red interval is our model uncertainty. So notice several very interesting things about the behavior of this posterior mean and the uncertainty. So notice that in these intervals, the uncertainty is essentially proportional to the noise, right? So you see that the width of this interval is almost constant everywhere. So in this case, we essentially deal with only the kind of noise-related uncertainty. Here, the uncertainty is related to the fact that there is a noise, and the noise is roughly the same as here or here, but also the uncertainty is larger because we are not sure about the functional form, right? So this uncertainty where the jump is results in a much higher uncertainty of the reconstructed function. It simply shows you that it doesn't know where the jump is located. We can illustrate it better if we take the same type of model, but now rather than having the noise of being 0, 15, let's make the noise 10 times lower. So if we do that, you can see that now we can barely see the noise, right? So it's a good idea to redefine the function because we never know kind of where the model is fully specified. So if we don't run it from the beginning, there can be some leakage of the parameter of the data, sorry. So we do the fit, we visualize our means and samples. So notice that now we can very clearly see that the noise is much lower because noise is much lower. We can very clearly see that there is uncertainty in the jump position. Or we can visualize it using this data. So this is obviously a small number of them. I show only 15. There are actually 5,000 of them. And this is how the uncertainty will look like. So in this case, the predictive uncertainty is very low here and here, and the predictive uncertainty very high here. So basically, once we have this type of prediction, the next natural thing for us would be to, if we were running the, if we were analyzing the data only, we are done. But if we are running the active experiment, it is very clear where we should choose the next measurement point, right? We choose the next measurement point and the location where the uncertainty, predictive uncertainty is maximum. If we want to solve the optimization problem, then we need to calculate the acquisition function, and we'll do it the same way as we did for the Gaussian process. Make sense? So the most important thing is to understand why does the blue line goes the way it does. So it looks nothing like the ground truth, but it simply reflects the fact that if our model has a jump, the jump can be anywhere between this location and this location. And since the jump can be anywhere in this location, the average of these possibilities will give us this segment. So interestingly enough, this is the most probable function, but these are the samples of the physically realizable functions, and these are the samples from what the data can be. They have kind of posterior predictive distributions. So notice one very unique thing about the Bayesian inference. So let's assume now that the noise is very, very high. So let me increase the number of points. So let's make 35 points. This is my noise. I define my models. I run my inference. A little bit slower than it should be. Okay, now we are going. So it will take a few minutes for us to less than a few minutes to get there. So let's rerun all of those. That doesn't look too bad. In fact, notice that the Bayesian inference has a remarkable property to be well behaved even when the noises are pretty high. Okay, that's actually a little bit too good. So let's go back to the back to the drawing board. So go back to the point where, let's say that we have 5 points and make noise even higher. So this should look horrible. Let's see if it is the case. It does look horrible. So let's see how the fit will work in this case. So now we're giving the data with the very small sampling and very large, very large noise. So obviously at this point, for this type of data, the fit through the least square fit would simply not be an option. It's just kind of unreasonable. So let's see what happens to the Bayesian inference in this case. So as you can see, it didn't work particularly well, right? It basically told us that the jump can be anywhere, jump can be positive, jump can be negative, and so on and so forth. So if we plot the uncertainties, it didn't work particularly well. So notice that the important aspect of this fit is that we used very open priors. So our ground truth function has the jump, which is located at 2.2. When I define my piecewise fitting function, I use the uniform distribution for the jump position, and I can say that this jump can be anywhere between 0 and 5. And when I do the fit, the jump is anywhere between the 0 and 4 because the noise level is very high. So look what is going to happen if I say that my jump happens exactly between 2 and 2.5. So this is a true value of, this is kind of very close to the true value of the jump position. So I can again run the code. So notice what happened in this case, that despite the fact that I have very few points and the data is super noisy, if I try to fit it, I get the function which is much closer to the ground truth. And the reason why it happens is because I have rigidly confined the jump to be sitting somewhere on this interval. If I choose the predictive uncertainty, then I mean it's very much off, right? Because it basically made this point is off and this point is off. So the noise is very high, but it is much better fit that I would be able to get using the least square or any other fitting function. In fact, if this was something that is available to you as the ground truth, you would say that the best you can do is to fit it by the straight line, and even this would be kind of squishy. The great thing about the Bayesian methods is that we can incorporate this prior knowledge, and even if this prior knowledge is that we know where the jump is, it makes the fit work much better. So let me make it a little bit less kind of extreme. So for example, let's make the noise 0.5 and let's make it 25 points. And so the noise is still high, but you can clearly see that there are two segments. So let's see what happens in this case. So while it is doing it, let's look at the one more thing that kind of helps us figure out what goes on. And this is so-called the posterior distribution. So when we formulate the model, we have the functional form of the model and priors. So prior distribution are usually marginalized, so they're defined as 1D. It doesn't have to be this case. We can make them joint, but 1D is convenient. But after the model converge, we can create the posterior distribution. Oops. So posterior distribution is the what we learned during the experiment. So before the experiment, we have model and priors. After the experiment, we have data. And with the data in hand, our prior distribution becomes posterior distribution. So generally, posterior distribution is a joint distribution for all parameters. So we need to choose what cross-section to visualize. And these are the example of the posterior distribution for the parameters that we have. So we have the jump point. So this posterior distribution means that the jump point can be anywhere between 2.1 and 2.4. So it's essentially uniform. This type of posterior distribution means that these two parameters, beta 2 and beta 3, are basically independent on each other. This type of posterior distribution means that the parameters are kind of correlated with each other, and it makes sense because beta 2 and beta 1 is the intercept and the slope of the linear regression, so they would always be anti-correlated. So while we talk about it, let's look back at our data set. So this is what happens when we have a Bayesian fit, when we provide the rigid constraints, narrow priors on the position of the jump. You can see that the fit worked remarkably well, even though the data is very, very noisy. If we try to do the same type of fit and our prior is broad, so instead of 2 and 2.5, we choose 0 and 4, let's see what happens in this case. Okay, we need to run this one. Okay, it still got kind of close to what we had. Generally, if we, it all depends on the number of the data points and the noise in the system. But generally, in this case, the points are such that the jump point position is very well defined. Generally, if we relax the prior on distribution on the jump position, the jump can happen anywhere. So for example, one way I can illustrate this effect is to reduce the number of data points, but I think you kind of get the idea of how it behaves and what is going to happen. So the next thing that you may ask is, but how do you know the model, right? So in this case, I have the data generated by the piecewise model and I fit it by the piecewise model. But I can do the same thing and feed the data using the sigmoidal model. So this model is kind of incorrect, but I can still see how well the fit will look like and what are the outputs. So you can see that in this case, the fit is actually fairly poor, but I can kind of illustrate the posterior functions. I can calculate the posterior mean and the uncertainty. Generally, if the functional fit is poor, then any epistemic uncertainty between the ground truth data and the chosen model start to look like the noise which is high everywhere over the parameter space. So this is not going to work because I have an extra parameter. But so any questions about this part? So as the kind of way forward, again, try to experiment with that because that's ultimately the only way to learn things. But the main idea is that we have the data. Data is generated by the ground truth process of some form. We don't know the ground truth. We just use it in order to compare it to the answers. So it is very good idea to develop a little bit of the kind of almost schizophrenic mindset, where we, on the one hand, keep the ground truth in mind, but on the other hand, we realize that the algorithm has discovered the system behavior without knowing the ground truth. So to implement the Bayesian inference, we need to provide the probabilistic model. So probabilistic model has the defined function and the priors on these parameters. Once we apply probabilistic model to the data, we run the Monte Carlo Markov chain Monte Carlo. So then we essentially, instead of priors, we get the posteriors on the parameter distribution. And then we get the functions that allow us to visualize what happens. So we get the sample predictions, what the data can look like. We get the predictive mean. So what is our idea of what is going on? we can look at only the functions to get an idea of what they are. And we can also calculate the uncertainties that can be used for the Bayesian optimization. And we can calculate the uh, posterior distributions, which basically tells us what are the outputs and how much we can trust them. So this distribution basically tells us how well we know certain value as the result of the Bayesian optimization. So for example, if I go back to the okay, this one is correct. So let me choose the data with much less noise. So this is the data. These are the models. These are the models. So I run my fit. Sorry, let me specify the execution. So let me choose the piecewise model. So I can run the fit. Give it a few seconds. So in this case, you can see that now the uncertainty, where is the jump? This is our posterior mean and the model uncertainty, and this is our posterior distributions. You will see that we get a much better idea about what the posteriors mean. So for example, the posterior distribution for the position of the jump is somewhere between 2.1 and 2.4. So why is it this way? Because we have 1 point at 2.1 and 2.4. So when the noise level in the system is fairly low, the jump actually has to be somewhere between those two intervals, but it can be anywhere within this interval. Therefore, our posterior distribution is almost uniform. Notice that it has nothing to do with the fact that we took the prior distribution to be from 0 to 2.24 because that has been very broad. So notice, by the way, a very important thing that I can specify the prior distribution to be very narrow but incorrect. So look what happens if I choose my prior distribution to be between 0.5 and 1. So in this case, I am certain about the position where the jump is, but this certainty is incorrect. So I'm basically confident in the wrong answer. So see what happens in this case with the with the Bayesian inference. So notice what happened. So the algorithm still tried to feed the data using the model we gave. We specified that the jump can be only somewhere here and it cannot be elsewhere. So basically the algorithm tried to fit everything to the left with the line, everything to the right with the line, and try to do it best to identify where the jump is. So the possible functions are basically consistent with how we specify the model. And we can look at the um, model uncertainty in the posterior mean. So as I mentioned, when the the uncertainty start to become almost uniform across the parameter space, that is an indicator that either our noise is high or our model is wrong, and then it kind of compensate for its wrongness by saying that I'm uncertain everywhere and I think it's noise. And oops, it's not going to work. And if we do something like this, we also get an idea of how the posterior distributions are going to look like. So in this case, they are going to have a considerably worse shape. So once they start to look something like this, so there is a clear tendency to move around and so on, that's also not a red flag, but a yellow flag that the posteriors are chosen, priors are chosen incorrectly. So anyway, this is it with the Bayesian inference. The next question you can ask is, how do we know, how can we select the right model? So it turns out that the way to do that is through what is called the widely applicable information criteria, or WIC. So let me illustrate how it can be done. So imagine that we have the same data set as above, but we don't know what is the right model for this data. So the way that we can work with that is to define a large number of the possible models. For example, we define a linear model, and with just one parameter, slope, and we define the prior for this model. We define a linear model with the slope and intersect, and we define the priors for this model. We define the power law, and the priors, and then exponential, and then same sigmoidal and piecewise functions. So then once we defined our models and their priors, and notice that priors matter because they define what we know about the system, what we can do is simply fit all those models to our data. So once we do that, we basically get the output for each model. For example, for the linear model, we get a beta and noise. For a linear model with the two parameters, we get beta 0, beta 1, and noise, and so on. So after we have done it, we can use a very convenient function called the WIC in order to, okay, let's wait until that fit converges. That allows us to compare how these models look like. So generally what WIC is, it's essentially the approach that looks at the Markov chain Monte Carlo. So it looks at our sampling results, and then it basically balances how well the model fits the data with how complex the model is. So those things are kind of go hand in hand. And then it basically ranks the models based on this WIC criterion. So as you can see that in this case, for this particular data set, the piecewise gives you the highest value of the criterion, which basically means that that's the right model. And subsequent models give progressively worse fits. So that basically means that we can say that given the data and the list of models with the priors, we can say that the piecewise model is the right model. So that's not a terribly big surprise. I mean, that's really not surprising in this case because we took the data to be fairly clean. And of course, we can estimate how the fit will look like. So this is the example. We, of course, can do the same type of fit with the second best model. So in this case, the fit will not be nearly as good. But again, we can see how it looks like. And based on that, we can make conclusions. So notice that there is another very important consideration is that in this case, WIC actually mixes the approach of Bayesian methods and the classical frequency-based statistics. So it takes two models in the Bayesian settings, but it compares them almost in the frequency-based way. If we wanted to do the comparison in the fully Bayesian sense, we would introduce the hierarchical model, which says that we have prior, that this is the probability with which this is a step function. This is the probability with which this is a sigmoidal function. So we have priors on probabilities of the model selection, and then we have priors on the model parameters. That would be the fully Bayesian approach to solving this problem. Unfortunately, it would be very time-consuming, and writing the hierarchical Bayesian models is kind of time-consuming. So the WIC was developed as the way to combine things and kind of make them simple and easy to use. And most of the time, it kind of works. So any questions about this part?
I have a question about wake. So how much does the complexity of the model penalize this wake metric? For example, let's say that we have like truly linear data, and we try to fit the data with a linear model and once with a quadratic model. Now the quadratic model has like one extra parameter, but if there is not like too much noise, a quadratic function would still be able to fit. My question is, would the wake metric still prefer the linear model over the quadratic?
So it comes up with a heuristic that balances the mean square error in both cases versus complexity of the function. So I obviously don't remember how exactly this balance is made off the top of my head, but generally the more complex the function is, the more it is penalized for being complex.
Okay.
So if the improvement in the mean square error between the multiple samples and the data is relatively small, then complexity is penalized. If the improvement is large, then it's not penalized.
I see.
So currently the field seems to be developing in the direction when we can choose the fits laying on some sort of Pareto front between the error and the complexity of the function. So these approaches are particularly developed in the context of the symbolic regressions, when you have a data and then you try to find the formula that fits the data best. But symbolic regression sort of comes with its own implicit ways of how you define the priors and so on and so forth. So you don't define them explicitly, but you can choose in which family of the functions you are going to look for an answer.
I see.
So there is always a balance of the domain experience and the kind of mathematical form, and it's very difficult to maintain it. That's kind of part of the reason why I strongly advocate for the domain scientists to learn these methods, because most of the time the knowledge that is required to be able to use them, from GP to Bayesian optimization to inference, is something that can be acquired relatively fast. So it's maybe a few months if you kind of focus on it, maybe even a few weeks if you're well familiar with the Python and some of the mathematical concepts. At the same time, the level of knowledge of the domain areas and the domain intuition that is required to choose the good models, that often takes kind of multiple years and tens of years to develop. And at some level, it simply starts to depend on what lab you're working on, how familiar you are with your equipment, and so on and so forth.
Okay, thank you.
So any more questions?
Can I ask a question?
Sure.
So if my question have a high dimensional input space, and I don't really know my ground truth and the minimal value of my functions, so how can I access or evaluate the GP model that I have built?
Yeah, well, that's kind of relatively straightforward. So basically, if your model is not one-dimensional, then you basically use exactly the same approach in order to put a two-dimensional model inside it. So there is neither for GP nor for Bayesian inference there is any intrinsic limitation on one-dimensional spaces. In fact, I will show you examples in one of the next lectures about how we can run a Gaussian process over 2- and 3-dimensional parameter spaces. So it's not particularly, it's not different. We are just going to, so for example, if I switch from, let me show you in a different function. Where is it? So for example, if we go back to our function that shows the GP for a fixed noise, you can see that the first argument that we use in the GP is 1. So 1 is basically standing for the dimensionality of the input space. If we choose the dimensionality 2 or 3, then we create the instantiation of the Gaussian process in the 2 or 3 dimensional space. Beyond that point, there are several kind of things to keep attention to. So first of all, technical limitation is that GPAX doesn't work very well for more than 3 or 4 dimensional spaces, simply because it was never written for those applications. But in those cases, there are 2 strategies. One is to use the deep kernel learning type of models that try to compress the dimensionality of the space, and I'll show you how it works. Another is to switch to the more complex ecosystem like BOTorch or what's not. The second problem is related to the practical considerations. So the practical consideration in these cases is that the reason why we want to use active learning is because it can make our experiment much more, or at least hopefully much more efficient in terms of how much data we need in order to get the answer that we want. So if our parameter space is high dimensional, it is always a question of how do we choose to sample that. So standard things can be the choice of sampling through the whatever Latin hypercube or any other sampling strategy in the high dimensional spaces. So hypercube can be better than grid search for a variety of reasons, but it's not that much better. It doesn't give us fundamental change in how many points we need. If we start to use the Gaussian processes in the high dimensional spaces, how fast we find the answer or whether we can find an answer depends on the complexity of our function. So generally, the Gaussian processes are advertised as they can be work much more efficiently than the grid searches. It's true, but this efficiency gain very much depends on how the ground truth answer depends. So if we have a single maximum or 2 or 3 maxima in our parameter space, Gaussian process will find it very well. But if we have multiple maxima, so we don't know anything about the behavior of the function, or it has some very sharp regions or so on and so forth, then Gaussian process will actually require a fairly large number of points. Not the same kind of, it will scale with the dimensionality almost the same way as the grid search. So sometimes it's not the case because GP can determine that some dimensionalities are important and some other dimensionalities are not important. So it kind of gives this advantage. But for pure GP, the benefit cannot be sometimes is not that significant. So it's factor of 10, but it's not a factor of 100, and then it gets worse with the dimensionality of the search space. In those cases, being able to use the models that have a physics component is usually a huge asset. So for example, imagine that you have a 10-dimensional parameter space, and you know that your 10 dimensions are concentration of components in the 11-component mixture. And you know that the dependence on the lattice parameter on the fraction of components is linear. This type of problem is exceptionally ill-suited for the Gaussian process. We'll spend a lot of time navigating 10-dimensional parameter space using GP, but this type of problem is exceptionally well-suited for physics-based exploration when we basically say that we introduce the linear model, we see how well this linear model works. If it works well, then our process is done. If not, then we introduce the deviation from the linear model, and then we kind of iterate. So the more we know about the physics of the system, the better we can work with the high-dimensional spaces. So practically, GP in high dimensions is very important in the theoretical problems, whether you solve theoretical problems or something where the amount of data and experiment is not that limiting factor, you can always get more. In the real world experimental problems, I typically work with environments when their experimental budgets are tens of experiments, or maybe hundreds of experiments if it is scanning probe microscopy, but definitely not thousands and tens of thousands. And I think that this is the rule rather than exception.
Thank you so much.
My pleasure. So any more questions? Okay, so then, so we're almost at the time. So for the next lecture, just as the heads up, we are going to talk about how the Bayesian inference and the Gaussian processes can be combined. So we saw the example of the Bayesian inference and that it works only in the low dimensional spaces with the correlations defined by the kernel function, which is limiting. We generally don't use any knowledge about the physics of the system. In fact, when we say that the mean function is 0, that's exactly what it means. We don't use any cheap information available during the experiment or any type of proxy signals. So in order to use, to get the maximum output from the BO methods, it would be great to be able to do either. So what I'm going to show is how we can take the Gaussian process, and rather than say that our mean function is 0, which is normally done in the Bayesian optimization community, we can incorporate probabilistic model similar to the models that we looked in the concept in the Bayesian inference as the mean function. And basically what it is going to mean is that instead of the prior predictive distributions that look like this, so this is kind of classical sausage diagram, our prior predictive distributions would be basically the functions that come with a certain shape. So we specify them using the functional form, much like we did with the Bayesian inference. And then for each parameter in this functional form, we are going to have the priors on the parameter value. So for example, if we have a function which has 2 peaks, we can, and offset, we can say that the offset has a uniform distribution from -10 to 10. The shapes of the peaks are like this. This is just a kind of almost Lorentzians. And we have certain priors on each of the parameters. So here they're chosen to be the same, but we can easily say that, for example, first peak has to be has height from 0 to 1, and the other has to be between 1 and 2. And the positions of the peak, here they're chosen to be from uniform from 0 to 1, meaning anywhere, but we can specify them to be much more narrow. For example, the first peak can be postulated to be here, and the second peak can be postulated to be here. So this combination of the Gaussian process and the structured model is exceptionally well suited for the solution of the problems where we know something about the physics of the data and some prior knowledge, and we also have access to the data. So on Wednesday, I'm going to show how they work, how they can be fine-tuned, and how to incorporate them in the real-world scenarios and kind of how they operate. So if no questions, then I'm looking forward to seeing all of you on Wednesday.
Sergey, I have a very quick question, or it's more like an ask for you. So I have to miss the lecture on Wednesday. Would it be possible that you post your slides after the lecture? Because
Sure.
I noticed that you posted like the day of the next lecture.
Yeah, I can do that, but keep in mind that they're also recorded, and the Acers give access to the recordings.
All right, okay, cool. Thanks.
So kind of without the recordings, they're considerably less useful.
Yeah, I understand. Yeah. All right, thanks.
My pleasure.
Bye-bye.
Okay, bye.
Thank you, bye.
Thanks, sir.